Hi everyone! After two introductory videos, there's time to start describing methods used in real-life analyses. You've learned that the true PDF we want to know needs to be binned so that there was a finite set of parameters to estimate. You've learned that the maximum likelihood estimators can suffer from a very large variance. Given that they have the smallest possible variance for unbiased estimators, the only way how to decrease the variance is by introducing a bias. Regularized unfolding biases the result towards a smooth shape. The assumption of smoothness is an obvious one, but the tricky thing is to ensure no real spikes on the true PDF are smoothed out. Each regularization method has a so-called regularization parameter that controls how strongly the smoothness is required. Let's not anticipate, though, and let's describe the regularized unfolding from its fundamentals. We start with the maximum likelihood method. Maximum likelihood estimators are those that maximize the log likelihood function log L of mu vector. The smoothness of the result is enhanced by adding a so-called regularization function S of mu vector to the log likelihood function. The regularization function is a function of just mu vector, and it doesn't depend on data. Clearly, the maximum of log L of mu vector plus S of mu vector is at a different point than the maximum of the likelihood function alone. The estimated histogram is simply smoother. However, the smoothing requirement mustn't be too strong because the data would be ignored effectively. Therefore, we need some way to control the relative importance of the likelihood and the smoothing functions in the expression we maximize. This can be done introducing a new parameter alpha, so-called regularization parameter. Alpha log L of mu vector plus S of mu vector. Let's see what happens if we set the regularization parameter alpha to some extreme values. If it's set to infinity, then maximum emphasis is put on the likelihood function, on the data to say, and no regularization happens. If, on the other hand, alpha is set to 0, then the data has no impact on the unfolding result because the only term that remains is the regularization function. Obviously, we don't want any of these two extremes. The final question to address is the choice of the regularization function. We will mention two options in this video. The first one is called Tikhonov regularization function, and it has the following form. S of f sub true of y is equal to minus integral over y, kth derivative of f sub true of y dy to the power of k. You can see it has an additional parameter, k, whose value must be chosen. Often, k is set to 2, and the result is a constraint on the average curvature of the unfolded spectrum. Tikhonov regularization is used in the SVD unfolding method in the RuUnfold package. The second form of the regularization function to mention is based on the principle of maximum entropy. The reasoning behind is the following. If all events of a histogram are concentrated in just one bin, then there is just one way how to arrange them, and the entropy is minimal. On the other hand, there are plenty of ways how to arrange the events such that there was approximately equal number of them in each bin. Therefore, a constant histogram has maximum entropy. So, the entropy regularization function biases the unfolded result towards a constant function. The exact form of the function used is S of mu vector is equal to minus sum over I going from 1 to m mu sub I over mu tot log mu sub I over mu tot. So, that's it for today. Next time, you can look forward to a completely different approach to unfolding, to a Bayesian unfolding. Goodbye!